Okay, here is an experiment dealing with the photoelectric effect. And of course, there's quite a lot of theory to understand here, so if you haven't seen the theory video, go and have a look at that first. However, what we understand by theory is that when light is shone in, a photon of light is shone in to a material, if the energy of the photon is greater than the work function of the material, there is an electron ejected with a certain amount of kinetic energy. So therefore, the energy of the photon becomes equal to the kinetic energy of the electron plus the work function. Or indeed, maybe a nice way of writing it is the energy minus the work function, the remainder gives you the kinetic energy max of the electron. And the reason why it's the maximum is because there is no other, it's just broken the work function, it's headed off, so that's the maximum. It could be smaller than this, sorry, if some of these are buried deeper into the metal. So what are we going to do, and how are we going to measure that kinetic energy? Well, what we're aiming to do is introduce into here, once it's been ejected, that electron, we're going to introduce a voltage. And note which way I draw that. And we'll say it's a variable one, in which this is the negative plate. So it's going to be shot off with kinetic energy. However, it's going to be repelled by that, and it's going to come back down to the other plate. The kinetic energy, of course, at this point where all the kinetic energy is just gone into electrical potential energy as it comes up to the top plate and drops back down, at that point where it just misses, we can say the kinetic energy equals the electrical potential energy, which we quantify neatly as the charge on this particle multiplied by the voltage that we have. We'll know when that just happens when this drops to 0. So when that drops to 0, we know that it's just missed that point. And therefore, we can say, let's just write in some values. We know the energy of the photon, hf, which is indeed the same as hc over lambda, because I know that c over lambda is f, the wave speed divided by its wavelength. I could rewrite this to be hc over lambda minus the work function equals EV. So there is a small manipulation of this original equation. Good, so I have a way of measuring that kinetic energy by measuring the voltage applied between these two plates, and I have a way of measuring the wavelength because I know the wavelength of light I'm going to shine onto this machine that achieves this, and so therefore I know lambda. So what I probably want to plot here is I probably want voltage, my stopping potential, should I call it, stop, is equal to, I'm going to divide through by E on all these fronts, is going to be equal to hc over E1 over lambda minus phi over E. Sorry, got the E in there. So if I were to plot my stopping potential against 1 over lambda, then what would I have here? Well, I would have, it is an equation of a straight line, y equals mx plus c. Of course, my intercept is somewhere negative down here, so my straight line would probably do something like that, of which this shows me that minimum potential, or the energy, I suppose that shows me the work function indirectly, because it will be hc over lambda minimum. So I can take that value, plug it into there, and work out my work function if I want to. And if it is a straight line, of course, the gradient will be hc over E. small rearrangements, we'll see if I can find out what h is, because I merely multiply the gradient by the charge on the electron divided by the speed of light, and that should give me Planck's constant. Okay, so quite a lot of theory in that. The equipment, you'll be pleased to hear, is a lot easier. But essentially what I'm trying to get is, I'm trying to get a table of results that looks a bit like this. I'm going to, first of all, let me show you the bit of equipment here. There is my bit of equipment. This bit here is happening in here. The light shines onto there, and it causes electrons to jump across the gap, and then I will see a current being measured with this one here. This, I can change the voltage to just stop it from going across the gap, and therefore I can measure the stopping potential because I have a voltmeter attached to there. I place over coloured filters, and then I shine incredibly bright light on it in order to illuminate that with only red light, or violet, or whichever filter I place in. So with that in mind, let me show you the table of results. Obviously I want to note the colour of the filter, and you'll see there as well the colour of the filter gives me a wavelength, nanometers, and that gives a range, so I'm looking for the average in nanometers, because you can see here it gives a range of wavelengths, so I'm looking for the average. Then I'm looking for the stopping potential, once, twice, 3 times an average, and then finally I'm looking for 1 over the average lambda. And I'll put that in meters to the -1. So that is my table of results. This is what I'm changing, the colour or the wavelength, which of course has a range, so my average wavelength, and then I'm looking for the stopping potential, and then finally I'm putting 1 over lambda, because of course I want to plot 1 over lambda against the stopping potential. Let's show you a few values. Like I said, it's a much easier system than it might have appeared in with the theory. But essentially, as I move this to 0 potential, we can see that the light falling on that is causing a current to flow, i.e. electrons are moving across. As I increase the potential, I'm looking for the point at which this just drops to 0, and then I know that the electrons are going up, but they're just missing and they're just falling back down, and that's the stopping potential. I can then place a filter on it, and of course we start this process again, but then illuminate it very brightly, and this is where we start our process off. So this is red to start with. So what's the stopping potential to stop red light? About that. Then it might make sense to go up in the wavelengths, so therefore I'll go for next orange. I'll need to increase a little bit more in order to stop it. Then sort of yellowy, and we'll continue the process as I go up a little bit in the potential to stop it, etc. And we just keep going along. Do it 3 times. The equipment could be simpler. The magic happens inside there. Here are the results. Fix on that again. Good, so I had my series of filters. I went red, red, orange, yellow, green, blue, and finally violet. The wavelengths had a range, so I just took an average of those. And then I looked at the stopping potentials. That should be 0.65, 0.56. And then finally 1 over them. And when you plot, you'll see you get that. And I worked out the gradient, and actually it was really close. It's the same order of magnitude. You're looking to achieve, with H, the real value is 6.63 times 10 to the minus 34 joule seconds, and it does reach that order of magnitude. Okay, hope that makes sense.